Our first keynote speaker today is Peter Davies. He's a director at Thales on security concepts. The title of his talk is Tolerating Individual Failure to Survive. Peter is technical director of Thales and their leading expert on cryptography. He currently concentrates effort on digital resilience and survivability and leads the security workstream for ASIN. He is security lead to Autodrive and RoboPilot 2 of the UKG research activities in autonomous vehicles. Over to Peter.
Thank you very much, Mike. That was my first 5 minutes. And I think that probably covers it. So this is basically me. I've been doing this for 30 plus years and all that. I'm currently centered on doing supply chain infiltrations and countering those and cyber physical attacks. But I started doing pacemakers. So if you want to find out about me, it's on the thing at the bottom there. And I really do believe these things are important, and we concentrate on security and safety. So these are the sorts of things I'd like to invite you to focus on, and thank you very much for inviting me to do this one. Some of the potential issues with V&V in the traditional sense, so the ways that we've been doing these things as we move towards larger systems. So Mike was talking about the fact that we've moved up from doing just chips and to looking at software and all the rest of the things. As I keep looking at vehicles, I keep concentrating on much larger systems than those, and really looking at that. So part of the observation there being that, often what we're actually looking at now is systems that deliver their effects at scale. So it's not the little bit of it, it's the fact that it all works together that turns out to be important, which comes from a different direction than sometimes we've concentrated on as part of doing these sorts of things. The handling of complexity. So it seems to me that's actually one of the really important things. Something that was simple when I was having to do 5 of it is not simple when I'm having to do 5 billion of them, and certainly not if I have to do it in 10 microseconds instead of 3 years. This turns out to be a problem. It's been a problem in science. It's certainly starting to be a problem into the sorts of areas that we're looking at. So there, time taken to do V&V as a factor in broadening the attack surface. So one of the things that I'm looking at there as a security person is actually the time we're taking to do the validation is actually giving me an area to attack things from a point of view of cyber attacks. And in fact, in many cases, it is actually one of the most prevalent areas that I find to attack things, because it means I get lots of time to practice. And you can't move, which is always good. And the need for our V&V processes to take into account and contribute far more fundamentally to avoiding catastrophic failures. So we've often been quite good at looking at that at the very small scale, but now what we're looking at is actually quite large scale systems. And it's not the fact that it's going to fail, it's the fact that it will fail catastrophically that actually turns out to be really important. So this aspect of looking at those sorts of things. And finally, the statements that we're actually able to make in relation to our components, our subsystems, and all of those things, they must be true in the face of active attacks. So because everything's online, because everything's joined up, because I don't get to do these separate things now, I'm getting active attacks against it. So it's not just a passive analysis of how does it all look. So that's what I'm planning to talk about. We do this one at the beginning here. This is the future we all want. I'm sure my component level thing is in there, so my chips, everything is part of this, but basically this is what we're all trying to do at some point, and if we're not, then some way we get encouraged to think about that. That's where my IoT is, this is where my smart buildings are, this is where my automotive, my power stations, more or less everything actually fits into that. We seem to be working somewhat more towards that, and it seems to me that this is part of what we actually need to, as an industry, have a way of actually discussing why we're not going to get into that situation. So I thought I'd put up a diagram here which actually goes in some way to, to trying to talk about the sorts of things that worry me and that has given me a way of talking about these things. So I used to talk in terms of risk, information risk, those sorts of things, and I found that people looked blankly at me. So nowadays I talk in terms of this is where you're going to be, who is the defendant, who's liable, who's the plaintiff, what court are we going to, and where are we going to go to that? Because that's kind of operationalizing the sort of things that we need to do out of V&V, the sorts of things we have to do out of safety and security. And I found that people actually understand that. and they definitely understand how much money may be going. I've tried to put up a diagram here that's actually is designed to try and put some tension into what question it is you're trying to answer with your V&V. So to try and indicate that if I had an accident in my white car, for instance, it may well be based on the car that was two in front of me that I knew nothing about. So the fact that I'd been perfect in my design on my car didn't necessarily mean that I didn't have this sort of a problem coming up. And that I'm attached to all sorts of things, from GPS systems, from timing, from all of these sorts of things in satellite systems that I had nothing to do with designing. In systems that are to do with the overhead gantries that the Department of Transport puts up, or into traffic signals. I then started to move out of that to try and talk about, and if you're looking at software, well, software is being designed in what I might call a software factory as opposed to a chip factory or those sorts of things nowadays. It's not in the same place. It may well have the malware. And to try and include into this some of the things that, for instance, might be to do with your machine learning algorithms, where, for instance, the chap over here in the right-hand corner may well be part of that, and the training data sets will never actually be in the system, but are actually fundamental to these sorts of things. And trying to answer that set of things at the top there in terms of, and what would that mean, and why did what I did contribute to making sure that we were in a better position, it's the question I ask myself more or less every morning when I get up. And it's surprising, because often I can answer why I have done a better job on this, but it is really difficult to answer why that therefore means that the system that is part of is doing a better job, or is in many ways more secure and able to operate correctly. I've also tried to talk about the fact that data is actually the new currency on this. Everybody talks about these sorts of things, but very often I'm still talking at the level of a communications protocol, or the instruction sets on my processor, and yet it's the data that I was worrying about. It's how do I put all of these things together? These sorts of things are the areas that we're worrying about. I do like this quote from IBM in 2015, 103 exabytes of data. Nobody generates 103 exabytes of data. Well, first observation is that is not people typing in 103 exabytes of data. That's the system generating it itself. So what you're really looking at here, and the reason I started to concentrate on the automotive system, is the first system at this kind of scale generating this kind of data that people want to sell. And that is not based on things that are being entered into it. So all of our thinking about IT systems, personally identifiable, they all go with things that people enter. This isn't that. These are things that are fundamentally behaviors in the first place. And I'm sure that that number must be much greater than that today, but I haven't managed to find a number for that today. So this is what we are. Connected cars, from my point of view, are part of a hyper-connected bottom-up system with emergent properties for which there is no guiding mind, which is awkward when we're trying to do V&V, because we kind of rely on requirements and what it is we're trying to test. But actually, if you look at the way systems go together, this is pretty much the way systems go together nowadays. There isn't a guiding mind for all of these things. We suddenly discover that this is really useful for doing something that we had no intention of doing with it when we put it together in the first place. We enable really small companies that have got some really good idea to utilize the entire set of things we put together. Those are the systems we're looking at. So our V&V must actually fit into that. It must allow us to make statements around that. And if it's not, then it's causing us a problem. And it yields its benefits at scale. This is a worldwide system, both from an economics point of view, but from an entire point of view. So NISA making a statement about their vehicle, that it was a power station, I think last year. It's part of an economic fight back to nobody's going to want to own a car. It's part of changing things so that that's an economic asset. But it means you fundamentally joined it between two parts of the system, and you can't draw lines around them in the way that as engineers we have wanted to do. So when you're doing the verification, this starts to be important. It's often very price sensitive. So the idea that we can go, it's okay, the things that we've done on aircraft or trains or things of this nature where it's mattered how we verify things, or, you can't apply that kind of model to how you're actually going to do these things because nobody pays for that. So you have to look for more appropriate places where you can get leverage into these things. and it's multi-vendor. And we're already seeing every day I open the papers, metaphorically obviously, and have a look at things where somebody has talked about how competition law is, for instance, requiring that people make decisions in a different way, or people are not happy with the way we're handling our data. So this thing about you need to not lock out people is starting to actually impinge on our areas, which came with the diagram there of I don't get to say that everybody has to do things in my way. I don't own all of that kind of stuff, and I have to be allowing other people to put things in there. So whatever my verification strategy is it better not to be around that assumption that everybody can be forced to do it the same way. It's increasingly integrated. So these aren't things that stand alone. So the key benefits, so everybody talks about automatic vehicles, but the key benefits don't come from that. The key benefits come from connectivity. The fact that you're sharing things. And that's a really important thing. And the cyber attacks are systematically downgrading the systems that we have, or components of the systems that we have. So they're reshaping whatever it was that we thought we put out there. This bit's not working, or that bit's not working, or it's all stopped working. Or the root of trust is no longer trustworthy. This is the world that our verification has to fit into, and we're trying to look for ways to do that. And we don't get to control the attack surface. The way we've done things on safety critical systems, the way we do things is to say, this is the line around it. Anything that needs to be really high integrity, we're only going to do this because we understand how to analyze 50 lines of code. But actually, because it's now joined up and doing things as part of things, it's questionable. And it's not I'm saying we can't do that, but I do think we need to question whether we can actually do that on a lot of the things that we're trying to do. And to me, understanding what's reasonable or semantically sensible for a component of a certain type is going to become important. But it's not even been a consideration when we're doing the V&V. We want to do something in the abstract where everything does the same. We want to see it as science in that way without having to understand its operating environment or what you were trying to achieve with it. Which I guess is me saying you need to understand the failure modes, not just in terms of the fact that it will fail, but what residual functionality you're going to leave in there when it has failed. And not necessarily at the lowest level. So going through these things, trust and security. People tell me about how we have ubiquitous security. They're very keen to apply these sorts of things. Obviously, as a security man, I'm very happy that you apply all of those things. I definitely think you should have security, whatever that is. But the point about that is they add exponentially to the cost of actually trying to verify systems, to the extent that very often what happens is people take them off. I've looked in the CAV environment, and so many of the systems that are actually going through, for instance, that are testing vehicle-to-vehicle communications, don't actually apply the security because it made it difficult. But actually, that was a failure mode. So these things here are actually increasingly becoming part of this. There are new types of cyber attack. And data theft isn't the main objective. The main objective is to have effects into these systems. So you're not talking about the things that people talk about when they talk about that. You're talking about denial of service against the braking system. You're talking about the steering happening sufficiently after you wanted to steer that it desensitizes me and I can't operate my car properly. So these are the sorts of things that you're actually looking at in terms of I was supposed to be verifying systems that didn't, that we're able to operate in that way. And that's complex. And we don't think about remediation enough. Is one of the things I keep saying. So these systems are going to fail. It's too big. It's got to fail. I don't know how to do anything at that level of complexity and not have it fail. So that question of how you're going to get it back, what you're going to look at and how you're going to make sure it fails properly turns out to be much more important than it was when we were looking at the smaller elements. And it probably calls for changes in the way we do V&V. Data-driven I've talked about. And the system is constantly in flux. So the calculations we did on the automotive system, if you regarded that as a connected system, suggests that the current update on the automotive system worldwide is about 1 every 10 microseconds. That's unfortunate if it takes you 3 years to verify a component. Those two things are clearly not in step. So what is it you're actually verifying when you do that sort of thing is a question we start to have to answer. Yeah, and we haven't tried to answer those sorts of questions in our verification strategies. But it's really significant. We can't take the benefits of digitization. And everywhere I look, I was on a round table yesterday. Yeah, everywhere we look, these are massive amounts of money. These are massive societal changes that we're looking that are dependent on managing to get these benefits from digitization. I live in Brighton. I rely on the trains getting through, and that doesn't happen if I can't get more trains down the same bit of track. These are all to do with getting these sorts of things. I've put up here diagrams, and I'm not going to go through it. They're essentially suggesting that what you're actually looking at when you're doing an attack, what am I worrying about, is these sorts of things. But I'd like to concentrate on the one on the left, on the left-hand corner there, because I think this is one of the things that is really important from the point of view of V&V. What are we trying to do? Is the first question that you're asking. So what is it that this thing that I'm trying to verify is supposed to be doing? And why do we need to do it? Is it an important question? If I don't know why I'm trying to do this, I don't know what standards I want to apply to that. But the third element out of that is the one that I have a lot of difficulty when I'm talking to people about. Why do you think you're positioned to be able to do this? Or how could that become into place? And if I require that the entire world stops, we colonize Mars and we get 2 years to actually figure this stuff out, and it's something that's going at 1 every 10 microseconds, it seems that it's unlikely that the strategy we're adopting is the right one, and we need a new one. And a lot of the things that we're talking about that have come from small scale ways of doing things, it seems to me we can ask, will we be able to advance our science quickly enough that we would be able to get? And if we aren't, and you don't think we can, and there's no foreseeable way by which that's going to happen, maybe we should look for a different way to do some of these things. So essentially, I know somebody explained to me about many of the cultures that have got one too many, as that is the counting mechanism, not 1, 2, 3, many. And we seem to be on the 1, 2, oh dear, I don't know. So we're on that element about what are we actually going to have to do when something comes in at this kind of scale. These are not mine. Actually, one of them's mine. But the other one actually is the pyramid of pain. How many of you have seen that? It comes from security, or it comes from a security guide. But part of what he's talking about there was the things that don't change very quickly in our attackers, in our cyber attackers, are things like their capabilities, the really tough stuff, the things at the top of that triangle are to do with tactics, things of that nature that they have in relation to that. They don't quickly learn new things to do. And the same is true for us. So essentially, when we're trying to work out what we're doing, and we're talking about many of the things we're going to do, we're doing things in the bottom part of that. We're doing things like we're trying to lock down IP addresses, and these are things that are trivial as far as my attacker is concerned. And we're trying to do that in a 30-year system. That's what verification means. We're not understanding that actually this is not something that my attacker cares about at all. So those sorts of considerations about what was likely to be an important concern are things that need to get built into the expertise that we have when we're doing verification. Because verification has to persist over a period of time. It is not a point in time, and that's one of the things that comes out of the digital attacks that I think we need to consider. Another one over here is just looking at, I tend to find that people talk about 1, 2, maybe 4 of those things going together. That's the maximum set of things that they set out to verify. But actually, as I said, the system is based on that combination. And worst of all, very often the application is now operating jointly between multiple things of which I am only a partial owner. So the understanding of what the rationale is and what all of those things look like is something we need to rethink, because we are testing things that work well but don't necessarily contribute to the overall outcome, which is good for me because I don't therefore go to court. I'm able to prove that my component works properly, but it's bad for the systems that they're going into. And it's costing a lot of money to do that. So maybe there's a different balance there that we need to be drawing. I try and put things down. The government took 47 pages to write its cybersecurity strategy. I tried to write what a cyber attack was in 2 lines there. The connected autonomous vehicle car capability will be cyber safe, and I tried to use cyber safe if and only if we have justifiable and enduring costs. That means some reason. So this is where V&V plays. It's not, I think it's a bit better, or I have no idea, but we'll change it when it all goes horribly wrong, those sorts of things. And enduring confidence, so that means over the period of time. So if you have a 30-year product liability requirement into this, that's 30 years you're supposed to be able to make that claim. I appreciate I'll be retired before then, so I won't care. But my successor will. That they will do what we expect when we expect. And you'll notice I'm not talking about security here. The security techniques are things that we use in order to try and make that happen, not on the basis of something separate. So trying to draw these things together, I think, is fundamental. And one of the things to consider when you're looking at digital attacks is time effectively is in the hands of your attacker. They get to do what they want to do at the time they want to do it, not when it's convenient to me. So the fact I found out how to break your system does not mean that I break it. I wait for the most inconvenient time, the time that I choose to do these sorts of things. That is not true when you've been calculating statistically neutral failures and things that went with in the way we try and do a lot of these things. And the collateral damage thing from Miller and Vasek there, I found very interesting, because essentially they said it took us 6 months to specialize an attack against every Jeep down to an attack against a single Jeep. And it's one of the observations about digital systems. They fail globally inwards, not from a single component outwards. So when you get a failure, you are, unless somebody does something, you're looking at things failing globally, which is unfortunate because under V&V, we tend to try and make everything the same to try and help them fail globally. So these start to be considerations that maybe we should be building into our strategies, not as an afterthought, but as a fundamental. If we're developing systems that we can't get to a level of verification that we want, then maybe we should be looking at what are we going to do when it fails. Much more fundamentally, it should be the starting presumption. This is how we do secure systems, as far as I can tell, safe and secure. This is Cracktish Valiag, that's the Maginot line at the bottom. Yeah, but it's essentially, most people recognize this, it's all, we analyze it in depth. I only went back to the Middle Ages on these things to demonstrate it didn't work then. But that's what we're currently doing. Yeah, we have the same sort of things. I have ASIL components, so it's this kind of level of, it didn't work on anything through history as far as I can tell. But it's the strategy that we're adopting in relation to how we will win against our attackers. So one of the things I ask people to consider is, if you imagine that we've done it all correctly, and we've architected it, and we've coded it, and we've analysed it, and we've done all the V&V, would that mean, therefore, you were cyber safe and you'd be happy to take that to court? Because there seems to be some presumption if that's the case. And I think when people say they are, often what they're saying is, I will be happy to take my component to court. Yeah, my chip, but not, I will be happy to take the things of which that is a part to court. And you need to ask that question, or I think we need to ask that question as we start to develop systems going forward. Here, I invite you to consider, that essentially you often have conflicts in this. So I do this from a cybersecurity point of view, safety, personally identifiable information, stuff I want to make money out of. Some of those things I absolutely want to encrypt, others I absolutely want not to encrypt. Yeah, and yet what we talk about is security as though it's encryption or any of these sorts of things. If I've encrypted the CAN bus on your car, not that I would recommend that, and I lose the key, I can't decrypt the CAN bus on your car. I now have no signals. I have a very dangerous weapon there. And those are inherent conflicts. So what we know in our systems is there isn't a way to finesse this away. There isn't some right answer by which it all goes away. This you can look at later, but essentially this is people saying we do not have the science to do these things. These MIT Lincoln Lab, I rely on them, they're good guys. We don't have the science to do these sorts of things. So if we don't have the science, what we need to look at is doing something that we do understand. And that, to me, these three things in the corner here are talking about things that are conflicts. Everything works properly, but it stops something else working. Machine learning algorithms. Yeah, these fit as part of the verification. And the main point that goes with these things is observing that when I'm verifying things, if you don't have the science to actually understand what you're verifying on that, then you're going to be in a situation where you're making presumptions about statements you're making that are not true. I put this up because I like to see this as a real-time destruction of a classification algorithm based on poisoning a single point of attack. You remember on that first diagram we drew, we said the training data is not in the set. It's not there. It's not available to you. How do I even know what's going wrong? And yet we verify that and suggest that that system's okay. So this is actually summarizing the same sorts of things. Digital systems, easier to compromise as a system. Component compromises learned elsewhere. Yeah, open source, we all know about open source. I see it in the health service. I managed to get it in the automotive sector. These sorts of things will occur in all sorts of places. Brought together at the time of your choosing the attacks, tendency to monocultures. Yeah, you recognize all of these things. They all are interconnected. No single design vision. And you're using techniques that you don't understand. This is what we're trying to verify. So these ones here, our attackers love elements that we make static. And that's part of our mission in life, to make things static. So actually what we're talking about is, are we actually making things better or are we making them worse? With the techniques that we're using at the moment, do we need to move to much more dynamic verification techniques and things that are far less requirements driven? And I know that's sacrilege. It's certainly sacrilege to me as an engineer. But I've been forced to consider that possibly is what I need to be doing around a lot of these things. So what does it mean? They're increasingly part of hyper-connected systems. Existing V&V techniques may not be sufficient or legally sustainable. Bad news. If you do these things, you are going to end up in court at some point. And you're the guys that are supposed to know. You know, that was the conclusion from the VW case. Systematic failure must be avoided at all costs. The idea that 40 million cars stop one day and it takes me 6 months to start them again is not an acceptable outcome. It'd be good for not going to work, but not an acceptable outcome. Mustn't delude ourselves, by assuming, imagining that what we have assumed we have assumed requirements exist that can never be met, and recognise that there are inherently conflicting requirements in these things. Scale is a really important thing. New types of cyber attacks, data-driven, and it's not at all clear that V&V is composable. So it's not at all clear that because I check this bit, it actually means that that is any contribution at all. In fact, it may be a negative contribution to the system I'm going into. I remember listening to somebody talking on Formula One race about how they'd made a harder component and it had stopped everything else working because it had broken the stuff around it. And that was my last slide.
On time, thank you. So a great introduction to the day because it covers all the topics which we're going to be talking about today. Any questions? We've got time possibly for one. Yeah, okay. If you want to introduce yourself as well before you ask your question.
Thanks for the talk. I'm Alistair from Graphics Class at Imperial College. I enjoyed your overview of the rest problems we're going to be facing. I wonder, in your experience, could you point to maybe 2 or 3 things from the last few years in V&V that you think actually show potential or promise? So I think some of the building in some of the design concepts so that actually you're trying to randomize some of the outputs and things that come out of these things as a fundamental of what you're doing, and then verifying at the level of failure mode. So one of the things that we looked at there was actually looking at how we may have got it wrong, but we get 2% failure on a system, not 100% failure. And there were a number of techniques, it takes a little bit too long to go, but we'll talk separately, that actually looked like they were emerging.
as things that could be done that certainly to me look like they got some promise going forward.
Thank you. Well, the last question.
Hi, Chris, Smartports. You talked a lot about technical hacks, but one of the big metrics for hacking these days is social engineering. Is there any work that you're doing towards safeguarding yourself against that kind of attack?
So yes, we've done some work, and had I spoken about the bottom thing on the triangle there, that essentially put people up as one of the major attacks that went with that sort of stuff. So I am interested in that, and there are elements there to do with trying to deny people access or deny access to you as a personality and a profile, and some of the things that you're trying to do getting into that. But I guess one of the things that has got my attention recently is interesting on whether you look at the trillion sensor networks and things of this nature, is actually the extent to which people are no longer part of these networks, and actually you get similar things actually coming out of those as an attack.
Thank you. Thank you for the questions, and again, thank you to Peter. Thank you.
Thank you very much.